Hi, welcome to the presentation. I'm going to talk about Polars. Polars is a new DataFrame library with an API for really fast analytics. My name is Richie Vink. I'm the author of Polars. I have a background in machine learning and software development, and I am part-time sponsored by Xemnia, the company I work for, which sponsors a large chunk of my time to develop Polars. So today I want to talk about these topics. One, why Polars? Two, about the foundations we build upon with Polars. Three, about Polars performance, which is really good. About one of our key selling points, which is the expression API. And I want to finish off with a small example. I want to talk a bit first about why Polars, and then I want to do that by looking at current DataFrame implementations in Python. This is Python oriented, but the same may apply to other languages as well. One of the problems is that approximately 50 years of relational database design and research is not really applied in the data science community, as in not in the single machine tools. It is in big data tools because there you have to. But on the single machine tools, it's not really the case. That means we have eager evaluation. Almost all implementations are eager. And because of this, we don't have any query optimization. As a result of that, we have very large unneeded materializations of memory, which become really expensive once you go to a reasonable data size. And the responsibility on writing fast, memory efficient code is laid to the put on the user more. And most users are domain experts, but not really data analysis experts and not query optimization experts. And they have a terrible memory representation of string data, which equals to terrible performance. And how did we got here? We got here because we finished with something that was already there, which was really good in what it did, which was NumPy. NumPy is really good in numerical compute, but it's not intended and not therefore also not really good at relational compute. For instance, there's no missing data. As a solution, Pandas used the floating point, not a number for this, which is ambiguous at least, say the least. Not a number can mean the floating point, not a number. It can also mean the data is missing and you don't really know which one of it is. And it can also lead to strange calls of column types. For instance, if you start with an integer column and some operation results in that integer column having missing values, it may be casted to a floating point column to add the not a number types in there. There's no string data, and as a solution, they use boxed Python strings, which, if you want to traverse that array, is effectively pointer chasing. I will come to that in the next slide. There's eager evaluation. So that means there are no holistic query optimizations, and therefore there are huge intermediate materializations. For instance, Python strings in memory. So here we have a NumPy string, and if we put Python boxed strings in there, we have a pointer to the actual heap allocation. And if you traverse this memory, you're simply traversing the pointers, following the pointers, which will be a cache miss on every string read. Also means that you'll have a lot of heap fragmentation, and you will have quite some byte overhead per string value, which will also lead to some memory overhead. And in Arrow, those strings are tightly packed. So you have a data buffer with all those strings concatenated. We have an offset buffer, which tells us where the string starts and where it ends. And we have validity bits buffers. And this is a bit packed buffer, which tells us if a element is valid or if an element should be read as missing, null. there's another problem with current DataFrame implementation, and that's that Moore's law is ending. That means that single-threaded code is not really getting faster anymore, especially not 2 times faster anymore in the next 2 years. So as a solution, a lot of laptops, machines now have multiple cores. My laptop has 12 virtual cores, and if you go to the cloud, it can go to very large numbers. But at least I think almost everybody's laptop has at least 8 cores or something. And in my case, that means that if you run pandas, you run 1/12 of its capacity, of your CPU's capacity, which is wasteful, to say the least. Well, problems try to solve that by parallelizing pandas, but then you still simply, I say simply throw more, you simply throw more CPU power to the problem. It's not really simple. I don't think it's simple to build a parallelized pandas, so don't get me wrong. I just think that we can gain much more by rethinking the root problem. And if we simply parallelize pandas, we inherit all the problems. We still get the bad memory representation. We will still have a high memory usage, and we cannot really control memory. That was already hard when you go through memory via NumPy, but if you the higher you go into abstraction, the less control you have. And that's where Polars comes in. Polars wants to be a DataFrame backend query engine that doesn't have these problems and is really built from the ground up to be very efficient for in-memory queries and be very smart in how it does its parallelism. So Polars has got a front end, and the front end is available in Python, Rust, and Node. It's an abstraction over Arrow memory. I will get to what Arrow memory is in a bit. It's got a vectorized parallel query engine, and it's got a query planning. It's got query planning optimizations. This means that we can often choose to do much less work than needed. It's got a very powerful expression API. It's got copy on write semantics, but then actually a little bit better even. So that's why the plus plus. And we got very fast native IO readers and writers. So one of the foundations is the Arrow columnar in memory standard. And this is the future in large data communications, maybe already is. It's a standardized way of dealing with in-memory columnar data, but it's also a specification in how we can share this data over the wire. And this leads to a very huge decrease in serialization and deserialization cost, especially in distributed compute like Spark, for instance, where you need the data from one representation to another representation over the wire. You can have a lot of compute just needed to transform this data. And within the same process, because all these tools understand the same Arrow memory format, we can actually have zero copy interoperability. So for instance, Polars can have zero copy interop with PyArrow, with Ray datasets, with DuckDB, with Dremio, and likely a lot more tools. We use Arrow 2, which is a native Rust implementation. And because it's a native implementation, we can choose to use Arrow where we need it. But if we think we can do something different or better or smarter, which doesn't fit the Arrow project per se, we can still get a hold of the memory and do the things the way we like it. For instance, we use this a lot to prevent virtual function call overhead. Another foundation is Rust. Rust is a programming language that's really fast. It's as fast as C and C++, but different from C and C++. It's got really strong memory guarantees, and it has those thanks to the borrow checker ownership model. I'm not going to explain it, but it makes it a lot harder to get double freeze, get memory access you're not allowed to. So you have very strong memory safety guarantees, but you don't lose control. You can still fully control memory and make sure you traverse memory in a cache efficient way. And the same ownership model also leads to fearless concurrency. It's way harder to get data races, aliasing, etc., thanks to the borrow checker. An example of something we get thanks to the borrow checker is copy on write semantics. but then sort of special. So our memory buffers are atomically reference counted. That means that if you make a copy, we increment the reference count. And if the reference count goes to 0, we deallocate the memory. But the Rust borrow checker also guarantees that there are no mutable aliases. It means that when I own a piece of memory, or when I have a mutable access to that piece of memory, no other thread, no one else is able to write or read that memory. And that means that if we combine that knowledge with the reference count, and the reference count is equal to 1, then we know that nobody else can increase that reference count, then we're able to mutate that memory buffer. So this means we have end-free data sharing, free cloning, almost free, and we have mutable access when the reference count is 1 without a mutex. So that's something that's unique about Rust ownership, which we use in Polars and Arrow too. So in this part of the presentation, we will talk about Polars performance. Polars is really fast, and it thanks this to really taking performance in mind. It's not only about parallelism. With only parallelism, you won't get as fast. We get this by having fast cache-friendly data structures in Apache Arrow, but also very data structure-aware algorithms and cache-efficient algorithms. We really, per algorithm, we think about how we can traverse our data as cache-efficient as possible. We use work-stealing parallelism with a tool called RAM. And we have a lot of in-node parallelism. We have different parallelism. That's what I want to say. We have parallelism in the query engine, which follows a certain set of rules, which is predictable, but we have also parallelism per algorithm, which is less predictable because it depends per algorithm. For instance, in the group by, we have a radix group by and a partition group by. Which group by we choose for depends on the cardinality of the data. We will sample it just before we do the group by, and then we will make a decision. But for instance, in a radix group by, we will see how we can split up the partitions, split up the units of work best for that group by operation. And the same for a join operation and for partition group by operation. So per node, per operation, per algorithm, we will think, okay, how can we split this work up best? And we also have SIMD operations. SIMD stands for single instruction multiple data. That means that if you do, for instance, some arithmetic on floating point numbers, and to do a plus, to compute something on a floating point, it takes that amount of CPU ticks. In the same amount, approximately same amount, you do it not on a single floating point number, but on a whole vector of them. For instance, on 16 floating point numbers at a time. So this is on the same thread. So this is sort of in a thread, you have vector lanes, which is sort of parallelization of that work on a hardware level. And we do query optimizations because often the best work is no work. So if you can prove you don't have to do something, or you can do something smarter, go for it. And we have native I/O, which means we often can really read and write most efficient without any extra copies, because we really know where our data is, how it should be. We directly write to that data in the most efficient way. And this differs, for instance, if we have pandas and you want to read a Parquet file and you use PyArrow, first PyArrow reads that Parquet file into Arrow memory and then needs to copy that data into pandas itself. So you always have a double copy there. And here we see the results of H2O AI's database benchmark. H2O AI has done several benchmarks with different tools, also not the least tools. So Polars is in there, for instance, data table, our data table, which is a really fast DataFrame implementation. The ClickHouse, which is a vectorized database. Spark is in there, Spark on a single machine with in-memory data. So all these tools don't operate on disk here, but they operate in memory. Julia DataFrames is in there. Dask, Modin, dplyr. So yeah, there are quite some DataFrame implementation, but also databases, QDF. And here we see the results on the, there are different questions. So we have different questions for the group by, which start with easy questions and then with more advanced questions to really show that, to increase the complexity. And here we see the summarizations of those results. And we see that by summary, by the aggregate of the results, Polars is the fastest. It's twice as fast as the next in line with the join operations. And in the group by operations, it also does really well. And besides the sheer execution speed, Polars is also very memory efficient. So here we see a zoom in on the group by operations. And we see here the dataset size ranging from 500 megabytes to 50 gigabytes. And on the 50 gigabytes data, only Bodo.ai and Polars were able to finish it without going out of memory. But Bodo.ai needed 128 cores to be as efficient as Polars is on 16 cores. And Bodin, if I recall correctly, does JIT optimization and scaling of pandas, whereas Polars is just written from scratch to be efficient. And you really, this shows that you can get a lot with less. This part of the talk, I want to talk about Polars expression. Polars is one of these, Polars expressions are one of the selling points of our API. And that is because we really strive for a small API surface. We want to provide the user with composable blocks, which are really powerful, allow you to control what you want to do, but still have performance. So in my experience, often the case was in, for instance, pandas, that people who wanted to do something slightly more complicated, they were needing lambdas. And once you start using Python lambdas, you're running Python bytecode, you're killing parallelization, you have the global interpreter lock. This is a no-go for Polars. We want to prevent this as much as possible. So we want to give you the API that should be able to express what you want. And this is similar to the vocabulary of a programming language. The vocabulary of a programming language doesn't have to be big. It's actually quite small, but still is very powerful because of the combinatorial explosion. You can express anything you want. And the expressions of Polars are the same. So an expression is a type where you have a function that takes in as input a series and produces a series. And because the input and the output are the same, this means you can compose them. You can compose them indefinitely. And this is the power, because this is really, you can combine them as you want. And the series as input can represent different semantical things. They can be a column in a data frame. They can be a group in a group by operation. They can be an element in a list. And they will likely be more semantical things in the future. These are the ones we currently have. And this is a slide where I want to show this composability, the flexibility. So here we take a column foo and we sort that column by another column bar, and then we divide that by the sum of the column hen, yet another column, but only where the column hen is equal, or no, where it's larger than 19, where the column span is larger than 19. So this already takes 4 columns, some predicates, some sorting, a division, and you don't need any. So it is very flexible. This will be ran by Polars on the query engine, and we will make sure that we will run this as fast as possible. But the expressions are lazy. That means they don't run by themselves. No, they need a context to run. And the context deals with the expression execution. So for instance, a context can be a select statement, it can be a group by operation, it can be traversing the elements in a list. But the context depends how we execute it. But the meaning is mostly the same. For instance, here we have a select context where we select columns from a data frame. And within the select context, every expression is embarrassingly parallel. So here we take the column foo and compute the rank. Here we have a when, then otherwise, sort of if, then else expression. And then we have a predicate, then we have an answer when the predicate is true, and otherwise we will take the column hen when the predicate is false. This expression will run also in parallel, and we have another expression which computes the difference, which will also run in parallel. All these expressions don't need any communication, so they can run in parallel. But there's also within an expression, there can also be parallelism. For instance, the when, then, otherwise has got 3 branches, so we can compute those branches in parallel. And a branch can also be really expensive, so it can be really pay off to do this in parallel. The context can also cache intermediate results when it thinks it needs to. For some more expensive expressions, such as window expressions, we do this. And I want to go to an example. So here I have a notebook open, and I want to go to an example of how we would use pointers and the expression API. So let's start simple with a data frame. So here I create a data frame with some distributions, just sampled from a NumPy, from the NumPy random function. Voila. So as we can see, we have distribution 0 up to distribution 7 with some sample data. And let's use the expressions to play with them. So I can select, this is not a really useful example, but I can select all the columns by saying select pl.all. Now I want to make it a little bit more useful. I want to add a column with the groups A and B depending on the predicate. So let's type it out. We say pl.when, which should add an expression with a condition. So when the column distribution 0 is smaller than 0.15, then I want the string value A, and otherwise I want the string value B. And we want to call this column groups. Voila. And I need to add a comma at the end. And when we do that, we will see we have this column groups, and we have it as a first column because the order of selection matters. So we first select this column groups with the when, then, otherwise expression, and then we select the rest of the columns. Note that all the columns are, if we would select this from another data frame, we would just copy these columns by incrementing a reference count. So it won't cost you any extra data. Let's now make a utility variable selection, which selects all the columns except the groups. So we want everything except the groups. So we only want the distributions. And then we want to compute the sum of the selection. So this would compute the sum. But if we want to add another aggregate, for instance, the entropy of the distribution, and we would run this, we would get an error saying that we would have duplicate columns. So we can add a suffix because we would still want to keep the dist 0, the dist I name, and we add a suffix sum and a suffix entropy. And now if we run this, it all runs fine and it computes those. Note that this is all executed embarrassingly parallel. So you just throw something on the Polar's query engine and we will parallelize it for you. This, yeah, as you can see, it's really easy to parallelize over all columns. We can also complicate these expressions. So let's say our business domain says we need to compute the sum of the selection. Oh no, when the sum is bigger than 1, we want the entropy, and otherwise we want some other complicated expression. We want to compute the skew times the entropy times 10. Some weird business logic. Expressing this is fairly easy with a when then otherwise expression, and we can run this and it executes. But the same logic the same expression can also be ran over the groups in a group by expression. So the same expression can be executed over the groups and it's not a problem. The same knowledge of Euler's expressions that helps you select things from columns applies to group by operations. So it's really easy to make really complicated aggregations. Note that an aggregation also is parallel over the so let's compute the first of every column and add a suffix. This is also parallel over all aggregations. Voila. So also parallelizing in the group by context. So group by already does a lot of parallelization when determining the groups, maybe in partitioning, but also in evaluating the expressions themselves. We can compute this in parallel. And this is an example of how we can use the same logic to apply things horizontally. So let's build it up. So we say we have a select and we have our selection, which was all the columns distribution 0 to distribution 7, but now we want to compute something horizontally. So we can do that by concatenating all these columns in a list. Concat list selection. This would give us a list of all these distribution columns. And a list has got quite some strong guarantees that a list is homogeneous. That means that computing something horizontally like a sum on a list of floating points is valid. If we have a data frame can have strings, can have floating point numbers, can have dates, etc. It's not really even from the type data frame how we can sum this. That's why Polars doesn't like a data frame.sum axis is etc. axis is 0, because it's not really explicit that this will succeed. So if we have a list, we can take the R namespace and then the eval from evaluate expression, and in here we can take any expression. So we can take the same when then expression, but then we compute it over the elements. When the element is the sum of the element is larger than 1, then we want the element's entropy. And otherwise, let's take the first. I'm going to do it a bit shorter. Otherwise, we want to have the first. And then we see we get the aggregation, but still in a list. So let's say we don't want a list, we want a floating point column, we can just flatten the list. And voila, we have the result of a complicated expression. Note that we're using the eager API here, but Polars actually has two APIs. The eager API is very similar to the lazy API, only it doesn't do any query optimization. So it's always better to use the lazy API, which you can just switch between by just adding a lazy at front and a collect at the end. And we have the lazy API. And the lazy API is with the collect is very similar to Spark. You have a computation graph, and we delay execution until you request this execution. So let's continue with a more straining example. Here we have a here we have a CSV from the yellow trip data set. It's a CSV with taxi trip data. It contains approximately 50 million rows and 18 columns, also with dates. So we want to scan this CSV. A scan CSV means we want to start a computation graph. We don't want to execute to running it immediately. And what we get is a naive query plan. So a naive query plan tells you what Polars wants to do, but it hasn't been optimized yet. So here we see we want to scan all, so the asterisk means all columns, all of the 18 columns, and we don't apply any filter at scan level. Then we will do a filter. So we filter any trip duration that's longer than 4 minutes, and we filter any unit of distance that's larger than 1. It's just something arbitrary. And then we have a naive query plan with those two filters. Those are not really optimal because those filters should be combined. That would be better because then we only would have 1 materialization instead of 2, because it's pretty expensive to materialize those intermediate data frames. And maybe even better, we're doing the scan at the CSV, would be doing the filter at scan level. So you don't have to materialize it at all. And then we want to do a group by vendor ID and payment type, and we compute some statistics. So here we compute the mean trip duration per vendor. And here we compute the maximum number of passengers on the 31st of January. So we have a condition where the drop-off date time is between 31st of January and the 1st of February. And then we compute the max of that, and we call that the maximum passenger count of that day. And if we request show graph, then we will get the optimized query plan. And in the optimized query plan, we see that we do the aggregation. We have an aggregation node, and we have a scan node. And the scan node only scans 6 of the 18 columns, and does filtering already at the scan level. That means we need to materialize far less rows than needed, but also far less columns than needed. And if we run this, so we can run this, and I do want to run this, but I also want to show memory usage while running this. So let's move myself here. So here we see my threads, my thread counts, and here we see my memory. And if we run this, we just call collect, and Polars is done in 2 seconds. And as you can see, we have a bump, and all threads were fully utilized. So this is great. We really want to see all those threads used, and we see a small memory bump. So that means that's likely because we were able to do a lot of those filters at the scan level. If you run the same query without optimization, then we don't do these filters at the scan level, and we naively select all columns. Then Polars would be still pretty fast, but it would be a lot slower, and it would also consume a lot more memory. So here we see the memory consumption is quite a bit more. But let's compare this with pandas. So here we have the pandas query, and actually we have 2 queries. We have an optimized query where we are a bit smarter and tell pandas which columns we want to read, and we have an unoptimized query. I'm not going to run the not optimized query here because it will go out of memory. That shows how much more memory pandas is using. We will run the optimized query, and this will probably take around 40 seconds. And yeah, as you can see, if we look at the thread utilization, it's fairly minimum. It's 1 thread that's swapping every time, and I don't think this 1 thread is fully utilized even. So it seems that there is quite some system call overhead, and we see slowly increasing memory. I want to talk about Modin, which is pandas array, which really does a good job in scaling pandas and can really improve parallelization. So yeah, as we've seen, the pandas query took 37 seconds, almost 40. So I think Polars was, I think, 19 times faster here and used a lot less memory. But you could also, for instance, scale pandas with Modin, which is pandas array. And let's run the optimized query, otherwise we will likely go out of memory. And Polars does a good job, sorry, Modin does a good job in utilizing all the cores, but it uses a lot of memory because of the not so good memory representation of pandas. And we have a wall time of approximately 22 seconds, which is approximately 10 times slower than Polars is. So even with full parallelization, it really shows that thinking of how you should design your algorithms from the ground up does a lot. I mean, 10 times is a lot. And that also was shown in the Bodo.ai versus Polars benchmark. So that wraps up my my example. Let's go to the. I want to thank you for watching this presentation. And if you are interested in the project, please go to our GitHub or go to our Discord and send us some questions. Yeah, and have fun with the other presentations.